All right, so in this video, we are going to look at how to import some data from files, and we're going to look at some basic statistical functions so that we can do things like um, describe a set of summary statistics, calculate means and standard deviations, and other things like that. So to get us started with our analysis. All right, now I've created another script file in the same folder that I saved my last script file in. And I've also imported two data sets into this folder that I want to open in order to install, load the information into R and then do some analysis on them. Now, if you don't have your own data files, you can, as we did last time, load the empty cars file, and then you can do analysis on, let's say, the MPG vector that we looked at last week. But I'm importing this data for a particular reason because sometimes the data that's available to us is available in different kinds of file formats, and we want to be able to do that. And also, there are some sort of kinks that sometimes work out when you load data from that's already built into R. Sometimes you don't run into some of the problems that you will run into when you import data from other kinds of data files. So we want to look at that. Now, the first thing that we're going to do is we're going to install a package that allows us to read Excel files into R. And so, as we did last time, we're going to go to the Tools menu, and we're going to install the package Read Excel. And then run that. And again, you can see it was downloaded and then installed. And so now we have access to it. This was already installed on my computer, but here we are. Now that you can also write out this install packages read Excel, and that will also install the function for you rather than going to the menu. You can also do that. I did also want to mention we had one comment in the last lab video about creating comments in the labs into the script files, just it for yourself or to make sure that you have a comment where the code is not going to run. It's not going to treat it like code. Sometimes it's useful to add comments to your script so that you know what the scripts are for, who wrote the scripts, and when. Because sometimes you will lose the context. It'll just be a long time, and you're like, what was this file for? What was I trying to accomplish here? And so adding comments to your script about the origin of the script, what you were trying to accomplish with the script, will be very useful, not only to yourself if you're coming back and reading this many months or years later, but also to anyone else you might want to share the script with. You won't have to sit there and explain to them, like, what is everything about? You can send your script to a friend who's also trying to learn R, and they will have the explanations that you wrote to yourself also in the script file. So that is useful not only for yourself, but it's also generally considered good coding practice. Now, because I'm actually redoing labs that I have already created, my original script files already have all of those comments in them. And so I'm not going to necessarily replicate all of those comments all of the time. We're just looking at the functionality here. So you should add comments to your own script files as you see fit. Now, you can, again, type out the import functions and then use that as your way of getting the files in. Now, files that are already stored on your computer, there's actually a point-and-click way that you can do that in RStudio, and then RStudio will fill in the written commands. But I'm going to write out the commands first just so that you can see them, If you're working with an online tool that lets you write R script, you won't have the point and click versions. And you in some places you may not need to install these packages, or you may have more difficulty actually figuring out where the location of these files are. But in my situation, what I've done is I've put the files I want to import into the same folder where the script is, because it makes things just that much easier. So I'm going to import the first file as a data frame, and it's going to read the CSV file. This is a comma separated file. It's basically a text file where every column is separated from every other column by a comma. So there'll be information and then a comma and then information and a comma and so forth. Now, one difficulty sometimes with reading in CSV files is going to depend on how the files were saved. Because if you have special characters, for instance, and we're going to see that in this example, that special characters may cause R to import numerical values as strings instead of as numbers. So hopefully the person that saved the CSV file is thinking about this and thought ahead. But the file I want to import is going to be the CSV file that I have here. So I'm going to give it the name that it has in my file list, .csv. And this does not require the read Excel package. The next version of the file will. And so assuming that I haven't made any typos, I can run this. No such file or directory. It's probably not in the working directory, but we can fix that in a second. Yeah, so I had set my working directory to be R, and this isn't in the R folder. This is in the subfolder. So I need to specify that that subfolder is there. So tutorials and then the name of the file. And then if I want, I can change the working directory. Recall that we can set the working directory here, and then I would just be able to call the file from the folder that it's in, because that's the working directory. But if I'm not in the working directory, I can pull it out of a subfolder by adding the name of the folder here. And so then let's try this again. There we go. So that imported the data correctly, and we can see data 1. It's a data set with 500 observations of 9 variables. Okay, now if I want to import the Excel file, then I have to load my read Excel package. So we installed it earlier, but now I need to tell R I want to use this library. And so that will, again, this is a warning message. It's just telling me when the package was built. It did not prevent the installation. And then I'm going to do basically the same thing. I'm going to import data 2. And I'm going to use a slightly different function. It's called read Excel. Notice the distinction here. This has a dot. This has an underscore. Easy to get confused. And then I'm going to do the same thing. I have to set the subfolder, and then again, relative to the working directory, and then specify the name of the file with the extension. XX. And hopefully I don't have any typos and this will load properly. And let's see what happens. So run. Yeah. So here's my data 2, and also 500 observations of 9 variables. Now, again, this way of loading it in by typing out the command isn't the only way to load data. And that's, in fact, in RStudio, it's my least favorite way, is like typing all of this out by hand. So the other way that you can load data is simply to find the file folder that has the data on it anywhere relative. So your home folder is usually, again, your documents folder. And then anywhere inside any of those subfolders, you can navigate to it and find the data file. And once you have found the data file that you want to export or import, what you do is you click on it, and it will give you the option to either view the file or to import the data set. And since we want to load the data into R for us to do analysis with, we want to select import. And what this will do is it'll create a wizard. It'll give us a little bit of a view of the data that's in the data set. We can see basically like looking at it in an Excel application, and it will give us some code preview of how we want to import the data. Now, the nice thing about this is going to tell us which package that we want to use. So if we haven't loaded the package, it will do that for us. And it will give us the function that we're going to use. It's going to tell us the location, the string of where it's located relative to our working directory so that we can import it correctly without forgetting those subfolders like you saw happened earlier. And then it will also automatically add the view command so that you can, once you load the data, you can look at it. Now, the one downside to this is that usually is going to pick a name for the data file that's going to be somewhat related to the name of the file as it was stored on your computer. Now, sometimes this can be useful. Here it's doing X for Excel and then the rest of the file name. This is a really unwieldy data file name to use as you go through your analysis. You can keep it, but what I would suggest is actually, rather than just importing, which you can do, it will import the data for you. I would suggest actually copying and pasting and then making some modifications to this before you actually hit the import. But we're gonna let it import, and then we'll do the copying and pasting. So if you just hit import, and it's not going to go into your script file. Notice here's our view of it. It's actually just going to go directly into the console. Now from here, what I would say is either from here or from that previous screen, copy and paste this function into copy and paste the function into your script. And then from here, again, all of this will stay the same, but then change the file name. So that, again, here I'm just using data 1 and data 2. Use a data file name that makes sense through this analysis. You don't need it to necessarily match the file name if this is, I mean, because like I said, typing this every single time you want to call the file is going to be a pain. And so just edit this. Change the data frame name to use after importing. So I'm not going to run this since I've already imported it twice. But I'm not going to reference this crazy file name when I do my analysis. I'm going to use data 1 from the CSV and data 2 that I imported earlier. But again, just change the file name. And then that wizard, that import tool is very useful because again, you don't need to think about like what is the relative file location relative to where I am. Is my work relative to my working directory? What is my working directory? R already knows, and it will give you the correct relative address reference that you need in order to do the importing. All right, so we've had a look at our file, and I'm going to leave the file open just to reference it. We can also use the view function we saw in the last time and in this import example, capital V, in order to view either of the two files side by side. Now, another way that we can compare the files, because they really were built on the same data, if we were to open these in Excel, they would look basically the same. But what we can do is we can actually see if, in fact, the two files are identical by using this identical function. And what it's going to do is it's going to compare the files and element by element to see if they're the same. and it finds out if any of them are different, it will say that they're not. So if we run that, it's going to say false. Now, on the other hand, if I use this other data file name that we imported in place of data1, so these are imported from the same file in two different ways, that will come back as true because those are, in fact, the same files. But as I said, the CSV file was originally created from this Excel file. So what is going to be the problem? Well, I can look at the structure of the two files, structure of data1 and structure of data2, and I can begin to see the difference. And that is that in data1, all of these income values actually came in as character strings because the dollar signs are being treated as an indicator that it's a string and not as a number. Whereas in the Excel file, even though it's formatted as a number, that's only a format, and it's still being imported. It's underlyingly still a number, and so it's being imported into R as a number. And so that, in fact, is the issue with these two. The difference between these two files is that all the integers, the counts of the location or ownership, or these dummy variables that are standing in for the community names, those are all just integers. But these income values or the monthly utility payments, they are formatted as dollars. And so when that was converted to a CSV file, the dollar signs converted all of the outcomes to strings. And so R interpreted them as strings. But when you import the Excel file, you don't get that formatting problem interfering with the style, the kind of variable you get when you import it. So sometimes it can be useful when you have data files like this. If you run into this error, it's certainly possible to clean this up fully inside of R, but it may just be easier to open the CSV file in Excel, clean up the appearance, turn these strings back into numbers, get rid of the dollar signs, and then re-import the data from there. Or again, save it as an Excel file and then import it from the Excel standard. Excel, I actually find sometimes very useful for performing data cleaning operations because it is sort of set up to do these kinds of interpretations and be as convenient as possible. R gives you a lot of control, but sometimes that means that you need to do more of the work yourself. And sometimes just for efficiency, we can lean on things that are already built into Excel. All right, now, sometimes I need to modify my data. Maybe I have a bunch of things in my data that I don't actually want to analyze. So we're going to continue the rest of this analysis with data2 because that is the version of the file that did import all of our variables correctly. But this first column of data, this household, this is just a dummy variable standing in for the name of the family living in the household. It is not a variable that is worth analyzing. And so we can extract that data column from the data file. I'm just going to save a modification of my data file to itself, and I'm just going to remove that first column. Now, if I only wanted to extract the first column, then I would not have the minus sign, and then the 1 would just say this is the first column of my data frame. But if I want to remove it, I put a minus sign in front of it, and R is going to interpret this as I want all of the columns of my data frame except column 1. And so if I run this, and then I can look at the structure of data2 again, now that household column is no longer present in the data set. And so again, it's a dummy variable standing in for the name of the family. It's not something that I can really analyze. Now, we're going to do some statistical analyses on some of our data. And so, again, looking at our column names, some of our column names have only one word in them, which is going to be useful. Some of them have spaces inside the names, which is going to require us to treat them specially in R. So let's start looking at just the simple case when there are no spaces in the names. We saw with empty cars, I can perform analyses on one column at a time by using the $ and then the column name. And so I can do things like the mean of data 2 and let's say the debt column. And I can calculate the median of data 2 and the debt column. And I can calculate the mode, if it exists, of data 2 and the debt column. And if there's no mode, then you won't get an outcome. And for numerical values like dollar amounts, that is a very common result, is that you don't actually get a mode. Now, for those columns that have spaces in them, a space is going to be read by R in like, here's a new thing I'm starting. So we can't actually do the spaces without putting some sort of collector around them. And so the tool that R uses is this backslash or this back apostrophe that's next to the 1. So if I want to do the mean of data 2's column on family size, I have to do this backslash, back tab, and then select family size. And notice, again, I can get it from the list and it will it'll automatically put those in. So that character right there that's surrounding this, these are not apostrophes or quotation marks, single quotes or double quotes. This is this back apostrophe, this backward little tick mark that's next to the 1 key on your keyboard. It's underneath the tilde. And so now if I run this, so those are going to reference that family size variable that has the space in it. And then I can likewise do the median data 2. And again, if I select it from the menu, R will automatically put those around it. And I can do the mode. And again, the mode. The mode in R tends to prefer categorical data, and it will give you the most common variable among categorical data. When you try to run the mode on family size, it will just tell you it's a numeric variable and it won't do anything. Now or it could mean that there's no mode. Now we can also do see what happens when there are missing values. So if you actually go to the data set like second income, I'm interpreting these missing values as being that there's no second income, but R is interpreting them as missing values. And so when you try to just calculate the mean, as we were doing earlier, data 2 second income, and then you just try to run that, it's going to say NA because it's trying to calculate values on things that don't exist. But we can just tell the operation, I want to ignore those NA values. So NA, this RM basically stands for remove them from the calculation, and then it will calculate the mean on the values that remain. So now we got a number. And so anytime you run into that issue where it's giving you an NA, it's because there are NAs in the values. You can always add this string. Typically, it's set to false by default, but you can always add this to anything that is not going to produce a value like NA. and it will remove the NAs from the calculation, and then it will be able to complete the calculation. Now, we can also do things like standard deviation, SD, and we'll just do det. And we can do the variance. And of course, the variance is the square of the standard deviation, so it's a lot bigger. And we can also do other common things that we might sometimes have to, in other contexts, calculate by hand. We don't have to calculate them by hand in R because they're built-in functions for things like the IQR. And recall that the interquartile range, the IQR, is the difference between the first quartile and the third quartile. So in other applications, like if we were doing this in Excel, you would have to calculate those two quartiles and then calculate the difference of them. And in R, the function's already built in. You can just call it and spit it out. Now, we might also be interested in finding particular quantiles for the data set quantile. So again, for a given particular variable in our data, if I run this, it will give me by default the quartiles. So quantile, it's spelled quantile, but by default, it will give me the quartile values. So the 5-number summary, the minimum, the first quartile, the median, the third quartile, and the maximum. Again, this, if you remember from creating box plots in basic statistics, that's the 5-number summary. You can also use the same function to get a specific quantile that is not on this list. So if I were to specify 0.9, then it will give me the 90th percentile. So 90% of the data is below this value, 10% is above, and that's my 90th percentile. So you would just express that quantile, the percentile value, in a decimal form. You can also request a list of quantile values. So let's say you wanted 0.025 and 0.95, 975. So this would be like your bounds on the confidence interval, for instance. And then it will give you both of those values for the quantiles that are in the list that you provided. Now, we're going to see eventually when we do non-parametric statistics that we may need to rank values in the data set by specifying this is the maximum value, this is the minimum value, and then ranking them from bottom to top in terms of their order. And so what we can do is we have a rank function in R, and again, we're going to do this on the det data to det, and we're going to specify, put NAs last. So that I don't think there are any NAs in this column, but if there are any NAs, you don't want them to be included in the ranks. So putting them last means that it won't affect the ranks of the other values. And then if there are any ties, you'll specify the method average. Again, this is typically what we use in non-parametric statistics when we're doing non-parametric hypothesis testing and we need the ranks. If we have two values or more values that are at the same value from different observers, then if they're tied, they're really not ordered relative to each other. We can order them however we want, and then because they're all actually at the same rank, average those results and give the average to all of them when there are any values that are identical. And so if I run this, again, I just get a list essentially of ranks. There's 500 of them. And so this is the ranking order of each of the individual observations. So the first value in the data set has rank 377. I can also do other operations that'll be useful later on in future analyses for setting up your own formulas for things. For like the length, not only the data frames, but also for individual vectors. And I can find out the number of rows or columns in my data frames. So if I use the function length on a data frame, it will tell me essentially the number of columns that are left in my data frame. So there's 8. If I apply this to a particular column in my data frame, data 2, then it will tell me how many observations are in that vector. So the length of the vector. And since there's only one dimension, it gives me by default the one that's not 1. But I can also, on the data frame, I can find out the number of rows and columns more directly. N row of data 2 is going to tell me how many rows there are in the data frame, and N col is going to tell me how many columns there are. And again, this is the same value as length, but length may be something that gets misinterpreted on a data frame. And so N row and N column will clarify that what exactly are we counting here. And then another really useful function is you can get a summary of what's going on in the data frame. And you can do this to one variable, or you can do this to the entire data frame. So this will give me, again, that 5-number summary, but also include the mean. Or I can do this to the entire data set. And then every variable will get the same treatment. It will get that 5-number summary plus the mean, the minimum, the maximum, and so on. If any of these variables turns out to be a string variable, then all it will do is tell me the count. It'll tell me things like the count of observations and how many different categories there are, things like that. So it will update in order to reflect the kind of information that is included in any particular column. Now, there certainly are other kinds of functions that we can use, and there are other kinds of packages that we can import that can summarize our data in even more useful ways. And so let's import some of those. So if we go back to our tools menu, we're going to install the package. What is it called? It is called HMIS. It's a package of, I would call it miscellaneous statistical functions, but this is the name. We're going to install that. And then similarly, there are some other packages that have useful functions in them, like paste CS. And psych. Now let's look at each one of these in turn. So I'm going to install or load each of these into memory. And then what I can do is in these functions, again, you can look at the documentation that you can find on CRAN for what all is included in here, but we're going to use the describe function. And so what the describe function is going to do is it's going to give me an output of statistical summary of my data set. And so it's going to give me a lot of information about things like the number of variables that are missing. So second income, there's 344, there's 156 that are missing, and 342 that are distinct. For instance, it's going to calculate statistical summaries on things like the mean and some common quantile values. So the 5th percentile, the 10th, the 25th, the 90th, the 95th, and so forth. And it's going to do that on all of the values where it can calculate those things. So again, this is a really useful function to just say, get a glance at what the statistics in the data set look like. We looked at the summary. It gives us some of this information, but not all of it. And so this gives us a little bit more information. This data set will also list the highest and lowest values in the data set. So if you're looking to identify any outliers, this is also a good statistical summary outcome that might be useful for you. If we load the psych package, and then we use their describe function, notice that the following object is masked from package hmisc describe. So now if I type describe, it's going to call the psych function describe and not the describe function that I used previously. So this will be a different version. Data 2. And this is going to give me a different kind of statistical summary. Again, the number of non-null values. It's going to give me mean. This one also includes standard deviation. It's going to calculate a trimmed mean. The MAD is the mean absolute deviation. So it's calculated using the absolute value rather than squaring things and then square rooting them back again. It gives me the minimum, the maximum, the range of the variables, the skew. So that tells me how skewed the thing is. If it's close to 0, that means it's nice and normal. If it's negative, it's left skewed. If it's positive, it's right skewed. The kurtosis is another calculation that you can do on the shape of your data sets that's usually ignored in a sort of common introductory statistics classes, but does help you identify the shape of the distribution. And then SE is your standard error using like your confidence interval, assuming this was a sample. Now, if I wanted to go back and use my other describe function, I can actually access it by putting the package name and then calling back that function. So even though the describe function from this package is masked, and I'm not going to run this because we've seen what it looks like, I can still call it back again by using this calling the function and then specifying with these double colons that I want to call the function from that package. And you'll notice as I started typing, it sort of filled those things in. It understood what I was going for. And then we imported one other package. And so let's look at that one. Paste CS. Now this one doesn't have the describe function. What it has is a function called stat DESC, which stands for describe, and data 2. Now this is producing output that's in scientific notation, which I find somewhat irritating. but it does include a bunch of information. So the number of values, the number of null values, it's going to calculate the minimum and the maximum and the range and the sum. Okay, the median, the mean, the SE of the mean, so that's that SE that was in the previous output. The confidence interval of 95%, that's the variance, the standard deviation, the coefficient of variation as well. So again, this is just giving me some kind of information about the variables in the data set, giving me a quick glance at the numbers. So for instance, this one doesn't give me things like the skew, but I could still compare the mean and the median. And if they're similar to each other, that would suggest it's probably not strongly skewed. Whereas if they are very different from each other, that would suggest that the data is probably strongly skewed. Now, another useful trick we can use is we can use the mean function to calculate the proportion of a 0, 1 variable. So notice that this variable just has values of 0 or 1, where 1 stands for they own their own home, and 2 or 0 means that they don't. If I want to know the proportion of people in the data set that own their home, I can actually calculate the mean of those zeros and ones. And it turns out that that mean is equivalent to the proportion of people that own their own homes, because you add 1 for every person in the thing that owns their own home, and then you divide by the total number of things in the data set, and that is just, in fact, the proportion. And so 56% of people in this data set own their own home. So you can get proportions of homeowners that way if you have these 0, 1 variables. Now, the last thing that we're going to look at is looking at the relationships between two variables. This is going to be very important when we do regression analysis. And so we can calculate the correlation. And here we would specify two column names that we would want to compare the correlation for. And I'm going to compare debt to family size. And so it seems like debt and family size are actually not very strongly related to each other in this data set. All right, so that is lesson number 2, and we'll come back soon with number 3.